our cars are going to learn to drive on their own. But that will not make any of us a better driver. Efficient navigation in the traffic, early detection of dangerous situations, evasive maneuvers that take you to safety. It doesn't matter that the deep learning algorithm inside your car is going to learn to perform these operations, as none of them will be clearly explained to you so that you, the driver, could take advantage of them when you're driving on your own. Well, some of you may say, but that's the point, to have a totally self-driving car to take you wherever you want. Professional drivers disagree. And they are right. They are right to be afraid of losing their jobs in the long run. But that is not the real problem. The real problem will be if they lose their jobs, and at the same time, we remain completely oblivious to the insights that AI obtained about driving and which made AI better than human drivers. It's not just cars and drivers that will be affected. PwC estimates that within just 15 years, about 1/3 of all jobs in the UK alone could be automated. These are no longer repetitive tasks on the assembly line. These are complex and varied jobs that require mental skills and flexibility. Aren't we interested why computers are becoming better than us in doing our jobs? Wouldn't we like to ask a computer, what do you know about my job that I don't? Fortunately, they can tell us. The world of efficient AI that performs the work well and also explains itself is possible. Ladies and gentlemen, my name is Jakub Gunner, and today I've got for you 4 stories about the alternative approach to artificial intelligence. 4 stories about the approach known as the explanatory modeling. So, what is explanatory modeling? What benefits does it bring? To find out, let's listen to the first story today, the story of discovery. The story of discovery begins with hurricanes. The last hurricane season reminded us how important climate science is. Climate scientists not only strive to understand which factors contribute to the formation of weather patterns, they are also equally interested in how these factors interact with each other to propel climate change over time. For a climate scientist, taking measurements can take an extreme form. Meet CCGS de Gruzel, a Canadian icebreaker that 20 years ago was turned into a research vessel and sent into the Arctic Ocean to conduct experiments. Over there, the ship remained stationary, allowed the water around it to freeze, and became the ice station Shiba. For 12 months, scientists on board collected the weather data and measured the exchange of heat between the surface of the ice and the atmosphere. This exchange of heat is known as the heat flux, an important factor in climate analysis. 12 months later, the mission was over, and the collected data were published as the Shiba dataset. Only 2 years ago, a group of scientists from Finland and Poland decided to use this Shiba dataset to challenge the established model of heat flux. The classical model, the one you're seeing on the screen right now, is based on only 2 factors: the difference of temperatures between the ice, the surface of the ice or Earth, and the atmosphere, and the speed of wind. The group of scientists 2 years ago decided to use a paradigm called genetic programming to better explain the intricacies of heat flux in the polar regions. They evolved a new equation that revealed an interesting pattern. It correctly identified the two main factors from the first model, the difference of temperatures and the speed of wind. However, it has also discovered the third, previously unaccounted factor, clouds. The model includes telltale signs of cloudy weather, reduced solar radiation, and humidity. This model is longer, yes. It is more complex, yes. But at the same time, it is also more accurate than the original equation. And because it was generated with genetic programming, it is explicit and transparent, and it makes the discovery of new factors so easy. How was it possible? How genetic programming was able to come up with such an equation that explains the reality so well? To find out, let's listen to the next story today, the story of survival. The story of survival begins millions of kilometers away from us, on the surface of the sun. Over there, a stream of particles escapes the gravity of the star and rushes in every direction. These particles are so powerful, they are a threat to all life on Earth. Luckily, our planet has got a defense mechanism that makes sure no one gets harmed. When the dangerous solar wind gets close to the Earth, it is transformed into one of the most spectacular views, the aurora. We know this defense mechanism to be the Earth's magnetic field. This field is so important that in the early 2000s, NASA was preparing to launch a whole series of satellites to study the properties of this field. However, they encountered a problem. They had to design a communication antenna for the satellites that would satisfy three seemingly conflicting conditions. First, the antenna had to support a wide range of frequencies for fast data transfer. Secondly, the antenna had to project a wide beam so that it could be easily captured from the Earth. And finally, the antenna had to minimize the electromagnetic noise coming from the equipment on board the satellite. The task seemed almost impossible for NASA engineers. How big should the antenna be? What shape should it take? No one knows. And then somebody had a clever idea. Look at life. If life could evolve on Earth and adapt to almost any environment, why can't we do the same with our antenna in the environment of space? What if we took some basic parts of the antenna design, try to assemble them in a semi-random way, and see which ones perform well in the simulated environment of space? What if we mimic the Darwinian evolution and natural selection inside a computer in search for a perfect shape and size of an antenna? A perfect set of antenna genes, if you wish. NASA engineers generated thousands of designs, most of them too weak and too fragile to sustain the hostile environment of space. But then there was one survivor. One design that could sustain the transmission of good quality and at the same time minimize the electromagnetic noise. Here it is. I know, it may look modest, it may look even random, but genetic programming was able to create an efficient design where human engineers struggled. Genetic programming gives us the power to mimic the Darwinian evolution and the processes of natural selection inside a computer. The end product might be an optimized hardware design, a piece of code that solves a particular problem, or, like we've seen in the case of our climate scientists, a formula that best fits the data. And so the story of survival ends with these two survivors. The formula that pointed climate scientists in new directions in their research, and the antenna that became the first artificially designed object to fly into space. You must be wondering, what do we, software developers, data scientists, the users of Spark, have to do with climate research or space antennas? To find out, let's listen to the next story, the story of curiosity. Do you remember when you heard about Spark for the very first time? Do you remember the passion and excitement when you were introduced to a new and great piece of technology? I do. It was on a conference like this one, Spark Summit, 2 years ago in Amsterdam. On the first day of conference, I attended the training sessions organized by Databricks. Do you know this feeling when you're trying to learn something completely new? You're struggling and trying, and you still don't get it. But you don't give up. You keep trying, you keep learning, you keep exploring, and then, out of nothing, you get it. All these maps and filters, all these RDDs and pipelines. It was a great feeling. So no surprise that when I came back home, I immediately wanted to complete my machine learning assignment in no other framework but Apache Spark. I loaded the data, I built the decision tree model, I was ready to go. And then I hit a wall. Even though I was able to classify new records, I couldn't see and access the model itself. I wanted to see the paths from the roots to the leaves of the tree, to see how all these decisions are made, how the data propagates through the model. And here I was, with debug string and root node as cumbersome ways to access the model itself. Today, I would have used a nice package called Spark Tree Plotting. You can find it on GitHub. But back then, Spark Tree Plotting did not exist. In the end, I used the Reflection API to access the hidden model and satisfy my curiosity. But I wasn't the only one. More people at the university took notice of the growing popularity of learning systems. Machine learning, deep learning. The problem was that whatever these systems learn is usually hidden, either by definition, like in the case of neural networks, or by APIs that do not facilitate the access. We shall do something about that. We shall take a step forward and build a system that not only learns, but also explains itself. A library based on explanatory modeling to drive us in new directions in our analysis. A library based on genetic programming to harness the power of evolution in synthesis of symbolic expression. And finally, a library tailored for one of the most thriving big data communities. Ladies and gentlemen, meet Lucid, an explanatory modeling library based on genetic programming and tailored for Apache Spark. Main features of Lucid will include transparent models in the form of rules and symbolic expressions, integration with MLlib pipelines so that you can use these models in your streaming and batch jobs, export of these models to scientific frameworks like LaTeX so that you can manually inspect and analyze these models, And finally, Lucid will be available through Spark packages. Right now, Lucid is under development at Poznań University of Technology. We are currently at the prototyping stage, but we have already secured funding from the Polish National Center of Research and Development. Krzysztof Chris Krawiec is the head of the project, and you can find more information about the initiative on this website. You must be wondering, is Lucid for me? Is explanatory modeling for me? Should I get interested? Should I get involved? To address these concerns, let's listen to the last story today, the story of trust. Meet Sherry Eastman. Last year, she came across a website called Beauty AI, the very first beauty contest in the world to be assessed entirely by artificial intelligence. Wait, what? AI assessing beauty? How come? How would it work? So first, Sherry had to submit a picture of herself, the one that you're seeing on the screen right now. Then this picture, like the pictures of thousands of other participants, was processed by 6 face algorithms. But these were not your typical face detection algorithms that you can find in your cameras or cell phones. These were specialized algorithms to assess the beauty of the face. One assessed the symmetry. The other one compared the face to some arbitrary standards of beauty, like faces of models and actors. And there were also 2 algorithms with interesting names. One assessed the complexion, and it was called the pimple. And another one assessed the smoothness of the skin, and it was called the wrinkle. A few weeks later, Sherry discovered herself to be one of the 44 winners of the Beauty AI competition, the ones deemed most beautiful by the AI, males and females, in 5 age groups. But Sherry also discovered that she was the only African American to win the competition. Most of the winners come from Europe, just a handful from Asia. And that's despite the fact that many people from Africa or India, for example, also submitted their pictures. This AI is racist, people complained. And look, we have to face it. The biases that exist in our society percolate into the AI systems we build. This is an example of a racial bias. Gender bias, here we go. There was an online system that displayed job offers for high-paying positions, more likely to men than women. It's already happening. But let's come back to where we started, the beauty contest. It's just a joke, right? We shouldn't take it seriously. Or should we? Let's listen to what the authors of the competition have to say about their initiative. First, they say, healthy people look more attractive despite their age and nationality. Well, maybe they do, but let's keep reading. Machines will be able to get a lot of vital medical information about people's health by just processing their photos. So that means that the assessment of my health and yours as well is not going to be based on professional medical examination, but rather on processing of ordinary pictures. It will be a dangerous world to live in. It will be risky to leave your home without makeup or unshaven, as your medical insurance or even pharmacy shopping could be affected. Luckily, European Union has got our backs. Next year, a new data protection law will come into force, GDPR. This law gives every citizen a right to question any decision that is based only on automatic processing of personal data. Do you know how media named this law? A right to explanation. If the decision is to be sustained, a thorough explanation of how the data were obtained and how the decision was reached is to be provided. You cannot always do it with a black box system. Trust requires transparency, and transparency allows you to detect and avoid bias. If you think that Lucid will be a viable alternative, please let us know. What is your use case? What kind of explanations will you need to comply with new law? You would like to know. Alternatively, if you think that right to explanation is a good business opportunity on its own, please get in touch. The team of Lucid is looking for business partners to develop the library and offer commercial support later on. So we are getting close to the end. In the story of discovery, we learned how explanatory modeling can be applied to climate science. The story of survival showed us how genetic programming allows us to harness the power of evolution. The story of curiosity introduced the tandem of Apache Spark and Lucid. And finally, the story of trust showed us how legal frameworks are catching up with the technology. These are just 4 stories, but there is more. AlphaGo inventing new moves and tactics that are now being taught in Go schools. A speech recognition system by IBM that has reached a superhuman accuracy. A computer vision system by Microsoft that is more reliable than humans in object recognition. Computers see things we don't see. They hear things we don't hear. They understand details we have little or no knowledge about. It is time we stop getting excited that we can just teach computers something. We should start getting excited that they can teach us. Because one day, I want to be able to say, we've built a fleet of self-driving cars. And thanks to that, we have learned something new about driving. My name is Jakub Gunnar, and I represent Poznań University of Technology. Thank you very much.
That was a pretty inspiring talk. Thank you, Jakub. We still have some time for questions, so there's a microphone in the aisle. If somebody wants to ask a question, go for it.
Hi. Yeah, thanks for the presentation. One question I had was, essentially you're talking about this explanatory models. Doesn't it limit it though to decision trees, right? Because even for genetic algorithms, how are you going to explain it, or explain it to GDPR? Let's say you used it for something. Or, I don't know, neural networks, for instance. You're not going to be able to use it with this approach. Is that right, or am I missing anything?
Yes, that's correct. The problem with, for example, neural networks is not that we don't have access to the model itself. We do have, but we've got many, many parameters inside. And, and they have no interpretation in the problem domain. To understand what these parameters mean, you need to understand how neural networks work. What we do, we try to operate only on parameters that have context and meaning in the domain of the problem that we are solving. So, for example, in the case of climate scientists, we operated on the physical variables. And yes, it limits us a little bit, but I think at the same time we gain a flexibility because we can combine all these variables that have meaning in our problem scenario in a completely various ways. And we are not limited by some formulas that are hard-coded into the model itself. I hope it answers your question. Okay, thank you.
Okay, thanks for a great presentation and interesting examples of stories. I was wondering, basically two things. The first thing I was going to ask is, can you give some example of algorithms that are built in Lucid and will be? And my second question is, shall I look at this package, more of the package with some set of algorithm, or as for the package that can work on top of my other solutions, helping me to understand the results?
Okay, so I'll start with the first question about the algorithms. Right now we are focusing on the genetic programming algorithm. And that's what we are building our prototype around. More algorithms will come in future. I'm sorry, I don't remember their names right now. But we can create models that are transparent, not only with genetic programming. So there will be more alternative approaches. If you follow this website, you can find more information and implementation details. And the second question, how should we look at Lucid? How would it integrate? So the plan is to use it in two ways. First, you can use it as a standalone library on top of Apache Spark to do your own explanatory modeling. But thanks to that, thanks to exporting of the models and compilation of models, because we can easily translate an equation from the mathematical form using quasi-quotes in Scala to a piece of code. And this can be compiled and used in your existing MLlib pipelines.
Okay, may I have
Yeah.
a quick first question? So it will be only available in Scala, or are you planning also to give the availability, for example, in PySpark for that? As there is obviously a huge community also in PySpark of data scientists.
Yeah,
Right.
we'll try to address and satisfy all potential users. But right now we are focusing on developing it in Scala, and once this is done, we'll go to other languages.
Okay, thanks a lot.
Thanks.
We have time for one more question.
Hi, thanks for the talk. I was just wondering if you could give us an idea of, I mean, even if I understand the ideas to make it more transparent than other machine learning algorithms, how does it compare these kind of approaches to, I don't know, if you were to try to design the same kind of models with a more black box algorithm? Because, for example, in the future, when we're going to have understanding of neural networks, then it's going to be harder for you to sell these kind of approaches if it doesn't perform as well as these neural networks that we understand how they work.
Okay. I think it's all about trade-offs. What is more important, a higher accuracy of a neural network or a comparative accuracy, but with explanation. It depends on basically what it is used for, on your business model and legal framework. If you don't really care about how it is done and what are the intricacies of the decision-making process, then you will definitely go for the neural networks, for example. But if you're more interested in explaining the decision, then then Lucid and the technology behind it will be helpful. Is that okay?
What if you can explain the neural network in the future? Like there's people working on, I don't know if you've heard about that, like heat maps telling you what kind of zones in images, for example, trigger the neural network. That's just basic work, but in the future we can have a better understanding of how they're working.
Yeah, that will be definitely really interesting, and it's a step in the same direction for clarity and transparency. So it's the same goal. Thanks.
Okay, that's it. We are out of time. Thank you, Jakub, and let's give him a hand.
Thank you.